Click the bell icon to get latest videos from Ekeeda.
Hello friends, in this video we are going to see a new topic, that is a flip-flop. What is flip-flop and where we exactly use the flip-flop? So before we start with the SR type flip-flop, we should know what is flip-flop is, how it is designed and for what purpose the flip-flop is required in digital systems. So let's see what is flip-flop is. Flip-flop is bistable logic circuit. Now bistable, we have discussed the bistable word when we have discussed the op-amp, that is a multi-vibrator. The multi-vibrator is a device which has a two states, two stable state is called as a bistable. Likewise, even in a flip-flop also we have a two stable states. That means your flip-flop will be either in a zero state or it can be in a one state. If it is a digital system, we always know that the digital system will work with the two types of input only, that is 0 and 1. Either it can be a high or it can be low. So basically flip-flop is also use a two types of input, that is a high and low, and accordingly output will be generated. So it will be either in a 0 state, this is called as a low state, or it can be in a 1 state, that is a high state. So it is called as a bistable circuit. Its output have a two stable states, that's why it is called as a bistable logic circuit. Second one, it is a sequential circuit. Now we have discussed what is sequential and combinational is. When it is a combinational circuit, then the output is depend on the present input of the system. But if it is a sequential circuit, then its output is depend on the present input as well as the past output. So basically sequential circuits require memory element to store the bit information or to store the information which is required as an input to the sequential circuit. Flip-flop requires a clock signal to be applied at its input for operation. Now there are few systems which are synchronous system and asynchronous system. When the clock signal is not applied, that time your output of the system is completely depend on the input changes. So whenever there is a change in input, there is a change in output. So this type of systems can be called as a asynchronous system. But if the clock signal is applied along with the changes in the input, clock should be present so that there will be change in the output. So basically output in a change can occur only when there is a clock present and there is a change in the input. So whenever there is a change in output according to the input, when clock signal is present, that particular system is called as a synchronous system. So flip-flop to be work, we should have the clock signal to be applied to its input along with the input data, whether it is a SR flip-flop or whether it is a JK flip-flop. So that we should care about what kind of clock signal we are providing, whether it is a positive edges, negative edges, like that. So we have a different types of clock signal. So clock signal should remain present so that that flip-flop should work accordingly to the change in a input. Different types of flip-flop. First type is SR flip-flop. S stands for set, R stands for reset. So whenever there is a two state, either the flip-flop can be in a set condition or it can be in a reset condition. So the name given to that particular flip-flop is SR flip-flop. Then JK flip-flop. There are few disadvantages which are associated with the SR flip-flop. To overcome this disadvantage, JK flip-flop has been designed. Now how this JK flip-flop has been designed, that we are going to see when we will separately discuss the JK flip-flop. Then we have a D flip-flop where D stands for a delay or data, and T flip-flop, the fourth type of a flip-flop, that is toggle flip-flop. So these are the name given to that particular flip-flop according to their working principle or their operation principle. So we will discuss each and every flip-flop separately. So here in this video we are going to discuss the SR, that is a set reset flip-flop. Now before we understand what is set reset flip-flop, we should know how this bit can be stored. Basically what we know is that flip-flop is used to store some information, and how this information can be stored, that can be understood by understanding the 1-bit memory cell. So let's see what is 1-bit memory cell is. So this diagram represents the 1-bit memory cell. That means in this particular diagram 1 bit can be stored, so the name is given as a memory because it is storing a 1 bit. Now let's see how it will happen. So basically we have a two NAND gate named as a G1 and G2. So we all know that if for a NAND gate, if the one of the input is equal to 0, suppose it is 0 1, or it can be 1 0, or it can be 0 0, or it can be 1 1. So for only 1 1 condition, the output will be 0. Otherwise, if 1 0, at least one input will remain 0, then output of a NAND gate will become 1. So that is how NAND gate works. We have seen the truth table of a NAND gate, so you all know how NAND gate works. So let's see what will happen here. Now to understand how it is storing one bit, let's see, we can assume the two case 1 and here case 2. Okay, so G1 and G2 are the two NAND gates where A1 is the input for the G1 and Q is the output of a G1. Similarly, A2 is the input for G2 and Q bar is the output of a G2. Now let's assume that in case 1, if Q is equal to 1, so here we can clearly see that output of a G1, that is the first NAND gate, is equal to Q, and output of a second NAND gate is equal to Q bar, and this Q and Q bar are a complementary outputs. That means they will remain complementary. If Q is equal to 0, Q bar should be 1, and if Q is equal to 1, Q bar should be 0. So here we have assumed that Q is equal to 1. If we have assumed that Q is equal to 1, then Q bar should remain as a 0. Now if we have assuming Q is equal to 1 and the 1 is applied to the input to the G2, because Q is nothing but it's an input going to NAND gate G2 whose input is equal to A2. So Q is equal to A2 is equal to 1. Now if 1 is provided to NAND gate, we have discussed that if 1 is the input given to the NAND gate. Now here we are assuming that the single input is provided to both the terminal. That means it is like this. So one single input is provided to both the terminals of the NAND gate. That means for both the terminal, the input is equal to 1. If input is equal to 1 1, the multiplication of 1 1 is equal to 1. But since it is NAND gate, it will invert the output and Q bar you will get that is equal to 0. So here our assumption is proved, that is if Q is equal to 1, Q bar I am getting is equal to 0. Now let's assume in the second case is that if Q is equal to 0. Now before that we have got Q bar is equal to 0. If this Q bar is nothing but it's an input to the G1, that is Q bar is equal to A1, that is the input of first NAND gate, that is equal to 0. If Q bar is equal to 0, which is applied as an input to the first NAND gate, if 0 multiply with 0, the output is 1. But since it is a NAND gate, it will invert the output and your output will be 1. So here it's proof that for Q is equal to 1, Q bar is getting 0. And if Q bar is equal to 0, Q will remain is equal to 1. Q will remain is equal to 1. That is what our assumption was. So here it's proof that it will remain in a state 1. If the Q has been assumed 1, that means the past output was 1. If we assume, it will remain in that state. Now let's discuss the second case where Q is equal to 0. If we have assumed that Q is equal to 0, again Q is applied as an input to the G2. If 0 is applied, that means output should be 1. So Q bar will be 1. If Q bar is 1, that means Q bar is equal to A1. That is also equal to 1. If 1 is applied, here the output will be 0. For the second case, that means Q will be 0. So hence prove that Q is equal to 0. That means if this particular diagram is in a state 1, that means if output is 1, it will remain in a 1 state. So that 1 state is called as set. That means if the output is holding 1, that means my diagram or my device is in a set condition, and it will remain in a set condition until and unless there is a change in a input. If you change the input, then only it will change its state from set to reset. And when it is holding a 0 state, that is our case 2, that is we have assumed is equal Q is equal to 0, this condition is known as a reset. That means if the Q is holding 0, it will remain in that condition for that particular time until and unless there is a no change in the input. That particular condition for this device is known as a reset. So either device will be set or it will be reset. So basically it is storing a 1-bit information, and this 1 bit can be either 1 or it can be 0 depending on the present input. So this is called as a 1-bit memory cell because it is storing a 1-bit information. Now this flip-flop, this is called as a flip-flop, this device, but this device is also named as a latch because if it is holding either set, that is 1, or it is holding a 0, that particular state is locked. That particular state is a latch. So due to its locking condition or latching condition, this particular device is also called as a latch because it is latching either 1 or 0. It is holding that particular information, so it can use to store a 1-bit information. So it is called as a latch because it is locking, and it is also called as a flip-flop. So this is how flip-flop can work. Now after getting the basic understanding of the 1-bit memory cell, we can move towards the SR flip-flop. Now let's see what is SR, that is set reset flip-flop is. Let's see how SR flip-flop can be designed. SR flip-flop can be designed by using either NAND gate or NOR gate. Here we have a diagram where we have designed SR flip-flop by using NAND gate. So here 4 NAND gates are connected together. Here Q is the output, and that is the output of NAND gate G3. G1 is represented, and where the input is given S, that is a set, and for a G2 input is given reset. Now if there are two inputs S and R, if you have a 2 inputs, that means you have a 4 combination. Your input can be either 0 0, it can be either 1 0, it can be 0 1, or it can be 1 1. This is the possibilities of an input to the SR. Now depending on the possibilities, we will check what is the output is. Now let's take an example that S is equal to 0 and R is also equal to 0. So if 0 is given to the NAND gate, now for both the input 0 is applied, that means output will be 1. In this case, similarly here also the output will be 1. Now if 1 is given to the G3 and G4, here you can see the 1 input is given as a 1, and here also the 1 input is 1. Now we know that for a NAND gate, if you have a 1, it is depend on the second one. If you have a 0 present, suppose this is the NAND gate, if 0 is present at one of the input, you can definitely say that output is equal to 1. But if one of the input is 1, you need to know what is the second input represents is. So we depends on Q and Q bar. So here you can see Q is connected as an input to the G4 and Q bar is connected as an input to the G3. So depending on what is the value of Q3 and Q bar and Q, the output of a G3 and G4 will change. So let's assume that first Q is equal to 1. If Q is equal to 1, this we can consider as a past output 1. So if Q is equal to 1, 1 is applied to the G4, that means we are having 1 over here. If both the inputs are 1, then output of G4 will definitely be 0. That means Q bar you will get 0. Hence proved, if Q is equal to 1, Q bar should be 0 because these two outputs are complementary with each other. Now if Q bar is equal to 0, 0 is applied to the input of G3. That is, suppose this is the 0. Now if I am having 0 at the input of the NAND gate, then definitely my output is equal to 1. If 0 is there, the output will be 1. So here I am getting 0 input. So definitely my Q is equal to 1. And that is proof that we have assumed the past output Qn was 1. So Qn plus 1 also getting 1. That means you can write you are getting Qn plus 1 is equal to Qn. So can we write over here that if the condition is 0 0, my output is equal to Qn. That means this condition is called as no change condition. We can assume for a 0 also. If we assume here that q is equal to 0, if q is equal to 0 is applied over here, the output of a G4 will be 1, and if 1 is applied over here, 1 and 1 will make out G3 output will be 0, and hence it is proof q is equal to 0. So we can clearly write that next output for 0 0 condition will be the past output, that is qn. Now let's discuss the second case with a green ink, that is 1 and 0. If S is equal to 1 and R is equal to 0. If R is equal to 0, then output of a G2 will be 1. Correct? And if S is equal to 1, output of a G1 will be equal to 0. Now for a G3, if we are getting input is equal to 0, one of the two input is equal to 0, then definitely output will remain 1. So I am getting Q is equal to 1. We don't need to check the other condition, because here clearly if one of the output is 0, then output will be 1. So here I am writing it's 1. Since we are getting 1, if we know that if 1 bit memory cell or that particular diagram with a logic gate is holding 1 as output, then it is said that it is in a set condition. So we can write this state of the flip-flop as a set condition. Now let's discuss the third case, that is S is equal to 0 and R is equal to 1. Let's say S is equal to 0 and R is equal to 1. If R is equal to 1, output of a G2 will be 0. If 0 is one of the input for a G4, definitely Q bar is equal to 1. If Q bar is equal to 1, Q is the complementary of Q bar, so it will equal to 0. Let's see it is getting 0 or not. If 0 is the input to S, so this output will come out to be 1. If 0 is Q bar and which is applied as an input, here also you will get 1. Let's concentrate on blue ink which represent this third case. So if 1 and 1 both the inputs are 1, then output Q will be 0. So here what you are getting as output is equal to 0. So since it is 0, that means your flip-flop is in a reset condition. If it is holding the 0 as output, then it is called as a reset condition. So this is reset. Now let's take the fourth example where S and R both are equal to 1. So here S is equal to 1 and R is also equal to 1. If S is equal to 1, here output will be 0, and if R is equal to 1, here also output will be 0. Now here you can see for G3 and G4, for both the NAND gate, your input is equal to 0. If input is equal to 0, output will be 1. Similarly, here also I am getting input is equal to 0. So here also the output will be 1. Now Q and Q bar, this both the output are tending to be 0. If both are trying to be at a 0 condition or a 1 condition, it is called as an undefined or prohibited state, because these two inputs are complementary with each other, and if they are complementary means that if one is equal to 0, then second should be 1. Correct? But here if we are getting the same output for both the input which are complementary to each other, this state is undefined and this is called as a prohibited state, or it can be called as a not allowed, because flip-flop cannot be used in this particular state. So it can be used either in a 0 0 state, or it can be used in a 1 0 or 0 1. So since we are getting set and reset condition, you can clearly see that if S is equal to 1, then it is a set, and if R is equal to 1, it is reset. So when it is a SR flip-flop, you should remember that if you are getting S is equal to 1 and R is equal to 1, it is called as a set and reset irrespective of what is the other input is. Now let's discuss what is clock make a difference to a SR flip-flop. Okay, so clock SR, in clock SR only difference is that instead of input is equal to S to G1 and R is equal to G2, we have applied one input as equal to clock. That means if you want this particular diagram should be work as a SR flip-flop, the clock should be present, and clock pulses are nothing but it's the pulses having the 50% duty cycle. So it can be either positive edge trigger or negative edge trigger. If it is a positive edge trigger, that means at positive going edge, the state of the flip-flop will change. If it is a negative edge trigger, then at the negative going edge, the state of the flip-flop will change along with the change in a input. So if you applied 0 0 as an input, your output will be remain qn, that is an unchanged state. But if you want to change the state from qn, that is a unchanged state, to set state, your clock signal should be present. If the clock signal is not present, then irrespective of what is the S and R, your output will remain at a 0 state. So your clock should be equal to 1 always. If it is a 0, irrespective of what is the S and what is the R, your output will remain at a 0 position. So if it is a clock driven flip-flop, you should apply clock signal rigorously so that your output state will change according to the change in a input, but the clock signal will be provided input as either positive edge trigger or it can be a negative edge trigger depending on which type of clock signal you are using. I hope you have understood the SR flip-flop, what is exactly flip-flop and how it can be designed. So thank you for watching this video. Stay tuned to Ekeeda. Do subscribe Ekeeda. Thank you so much.